Yes, we discussed the Voronoi diagram of line segments, but we can further have some different types of Voronoi diagrams. For instance, here you see some polygonal obstacles in the environment, and by following a similar algorithm, we can draw the Voronoi diagram of such a complicated field. As you see, these are not line or not points, and obviously, again, we should be checking the minimum distances. For instance, consider here, this one has a distance to the object here this much, and its distance to the other object is this much, and they should be the same. The fundamental is again the same, even the shape, the input is modified. And this resulting Voronoi diagram, as you see, a bit more complicated than the line segments or than the case where we only have points as Voronoi input. But the algorithm, the main algorithm, is always the same. And by using such kind of things, such kind of Voronoi diagrams, we can always generate a motion path for a kind of robot or a kind of a vehicle and try to find the shortest path or the safest paths. Now we'll have a look at some other types of Voronoi diagrams. We'll discuss some extensions. For instance, we may also have 3D Voronoi diagrams. This is, by the way, a low poly Stanford bunny. You may use this example in your fourth mini project, and you can see that some 3D Voronoi cells are generated. These are all 3D. And I have done this example on Grasshopper. It's not that complicated. You can also do the same. And then we have another extension. This time, we don't use conventional metric for the distance calculation, but instead we use L1 metric, or it's sometimes called as Manhattan metric. And it's defined as that the distance is equal to actually their distance between 2 points. Let's say this is P, this is Q. The distance equal to not the difference between their X and Y coordinates, taking their squares and then square root. This time, instead, what we do, take the difference between their X values and take the absolute value of them. This is the important part, and sum it with the absolute difference between the Y coordinates. This is our L1 metric or Manhattan metric. And once you use this metric in your Voronoi diagram computation, you'll come up with such a Voronoi diagram. And as you see, the edges of the Voronoi diagram are all horizontal, vertical, or diagonal. Let's look at here. I better use this one here. A horizontal line, a diagonal line, and let's find another one, vertical. Yes, here we have a vertical line. And in summary, the whole Voronoi diagram is consisting of just horizontal, vertical, or diagonal edges. We don't have any other complicated lines in different orientations. We can only obtain this one with the help of a special metric. This is called as Manhattan metric. So where do we use these Voronoi diagrams? We actually love to use them in modeling of different things. Even let's say from Apple, from the microstructures in materials, or different kind of things are easily modeled with Voronoi diagrams. Since if you properly distribute this Voronoi size, these are size, as you know, you may have such a grid pattern or an hexagon pattern or a random pattern. So the distribution, if the distribution is fine, you can obtain any planar subdivision. Here you see an example, for instance. We have many sides around upper side, but if you look at the below region, we have less of them, and that's why the size of the cells are larger. And these are examples for modeling of materials. These are microstructures, and you see we have an interface in between these two materials, and you can easily see it if I draw this line. Yes, and many people are using this kind of modeling to focus on different properties of the materials. You can also do meshing. Yes, Burak, this is also possible. If you properly distribute the Voronoi diagrams, meshing is also possible. Another application, people are trying to model fruits. There's an apple, as you see, and the interior of this fruit is just composed of Voronoi diagrams. They have some regions a bit different, but these regions are filled with water, these gray regions, but the original cells can be considered as Voronoi cells. And can simply put some sites here, and you may assume that these are the nuclei of the cells. We have another example in nature. Actually, you see some examples underneath, the cork example, some wood, sponge, even the bones, even the coral or cuttlefish bone. They can all be represented with the help of Voronoi diagram. So that's why it's quite important to use them in modeling, for modeling purposes. Another different study where they use Voronoi diagrams to study the statistics of salt. And these are some bubbles in the soap, and as you see how they are distributed. Now I will have some other examples from 3D printing or additive manufacturing. You see they use Voronoi diagrams to model the interior of the objects. And they are trying to increase the strength once they have some pressure upside. With the help of a proper distribution of material, they improve the performance of the parts. So another example, by modifying an interior, you can make it stand such objects. Initially, if you distribute uniform Voronoi diagrams, that will be the result. It will not be able to stand on its own, but once you have more material on the left-hand side or more Voronoi size on the left-hand side, you can make it stand. Another thing I want to focus is the case where you 3D, where you have 3D Voronoi diagrams inside the objects. And in this example, actually we have a kind of an cube shape, and this interior of this cube is actually divided into some Voronoi diagrams. Okay. Assume that this is an example, and once you take a slice, assume that this is a slice, and I will show you the cross section. Another thing, if you take a slice just a little bit above, we'll see that things are not modifying much. The sketch, the cross section is almost the same. So if you look at this is the previous one, and the next one is this one. We don't have much modification, just the vertices, the coordinate of the vertices are a bit modified. Sometimes you may have new edges appearing. If you, for instance, focus on here, we will have a new side appearing once we go with the next layer. You see? So what happens actually is that we have some cases that are just 3 of them. A new Voronoi diagram may appear, or an existing Voronoi, I'm sorry, not a Voronoi diagram, but the cell, Voronoi cell, might be appearing or disappearing. So this is a case where the cell is disappearing, or if you go in this reverse direction, you will see that a new Voronoi cell is emerging in the Voronoi diagram. Or the other case is that we may have such a kind of a flip between the edges. Once you move up in the next slice, you will see that instead of these two, let's say, edges are connected to each other, and in the next layer, they will be separated and be connected to a different set of edges. So you see we have, again, 2 vertices, but their intersections are different. It's not important. Some example work pieces printed having Voronoi diagrams. Any questions, guys, about this chapter? It's over. Now we are done with the Voronoi diagrams.
Teacher, can I ask something? But not exactly about this chapter.
Okay.
About the project. In our 4th project, are we asking to create something like that. We were given a 3D model, and by using the sites, we are going to create a Voronoi diagram and create the 3D model, right? In the fourth project.
Yep.
Okay.
You have such a shape, for instance. This is a kind of an igloo, and you will be given this igloo and the Voronoi size. And by using these Voronoi size, you will generate 3D Voronoi diagram, and then get the slices and have some kind of shells inside these slices. Assume that you have just 3 Voronoi cells, then I want you actually also obtain these shells. Okay. This is actually another thing. Actually, I have drawn it wrong here. We shouldn't have 3 edges. So once you do it like this, you'll only have 2 shells per Voronoi diagram. You see now we have 2 shells for each edge, and if you have an outer edge, this time you always also have double edges or double shells for the outer edges. But this one is quite wrong. You shouldn't start obviously with the Voronoi diagram. And depending on the case, I may want you have 3 shells, but it's a bit complicated. It's better you just focus first on 2 shells and then discuss other cases. I think you'll have even number of shells. It will be much easier. For instance, if I draw another extra shell around, you will see that we have 4 shells for each edge, right? So that will be the case I'm looking for. If you can somehow generate even number of shells, then you are fine.